All right, so we're going to talk about a new concept today called electric flux. We're going to focus on the word flux for just a second. Flux is a measure of the flow through a surface. So if we can think of like wind flowing through a window, you might want to quantify the wind passing through that surface. You might call it like the wind flux. We're going to do a similar thing with the electric flux. So the electric flux is the total electric field that's passing through a surface. I want to be a little clear here and say that electric fields don't actually go anywhere or flow through anything, but we can still think about how much of this electric field is sort of captured in a given area. And so that's what we're gonna think about through the electric flux. The electric flux, we're going to use the symbol phi sub e to represent the electric flux. I'm using the subscript e here to represent electric. We will see a magnetic flux in the future. So I'm going to leave this as phi sub e as the electric flux. And for a simple surface, meaning I can quantify the surface with a single area vector, the electric flux is given by the electric field dotted with your area vector. So let's see how this plays out using a picture here. So there's my electric flux again. And now I have this area here, and I have some electric field coming from the left pointing to the right. I can quantify this area vector, or the area, using an area vector. So I've drawn my area vector here representing the orientation and the size of that surface in space. And the next thing I'm going to do is I'm just going to extend my electric field vectors so I can see where they are in the surface and how, importantly, how they are oriented relative to the area vector there. And if I want to calculate my electric flux, I can go to my definition of the dot product, which is the magnitude of E times the magnitude of A is times the cosine of the angle between the two vectors gives you your dot product between E and A. And so here I have identified theta. That's my angle between the electric field and the area vector if they were placed tail to tail. And so now right away we can sort of see the utility of the electric flux. If my area vector is parallel to the electric field, that theta goes to 0, cosine becomes 1, and your electric flux becomes its largest possible value. If your area vector is now perpendicular to your electric field, so imagine just rotating this surface sort of this way, and so you can get your surface parallel to your electric field, your area vector is now perpendicular, you get 0 flux through that surface, right? And you can think about this using wind through a window. If you want maximum wind through your window, you should have your window oriented perpendicularly to the wind so that you are capturing the most wind through that area. And if you don't want any wind through your window, you should turn your window on its side and make it parallel to the wind so that there's no wind that can travel through the window, right? So a similar thing holds true for the electric flux, and we're going to use this in the upcoming section.